venu pour Raph, mais sinon je reste chez moi, oui.
Franchement, je pense que ce confinement, il va changer nos habitudes de travail. Hein.
C'est possible, oui, oui.
Ouais, ouais. Même si c'est vrai que c'est important de garder du contact social, notamment avec les doctorants. Je pense que voilà, il faut
Rahaf.
Yes, let me just put it in full screen.
Yeah.
Yeah, let me remove this.
Maybe during the presentation we can shut down the cameras. The jury member can shut down the camera for the as you want. We can attempt just to maybe to.
Ready to start, so I give the let's say the ball to the president. Please.
Thank you, Paolo. Good morning, everyone. So my name is Mehdi, and my colleagues designated me as the president of this jury. So today we will attend to the defense of Rahaf Rahal, and the title of her thesis is Shared Control and Automation for Robotic Operation. She was supervised by Paolo Rodolfo Gerardo and Claudio Pacelito. Sorry, Claudio. The jury is composed by Stéphane Régnier, professor at Sorbonne University. He was one of the two reviewers. Paolo Rocco, full professor at Politecnico di Milano in Italy. He was also a reviewer of the thesis. Dongheui, she's associate professor at Technical University of Munich in Germany. Me, I am a professor at University of Pi 8, and the two co-supervisors, Claudio and Paolo. So now we begin with a presentation of 45 minutes, and then we will take time for a series of questions and a discussion with the candidates. So Rahaf, you have the ground. You have 45 minutes for your presentation.
Thank you. Okay, good morning, everyone, and welcome to my thesis presentation. So it's about shared control and authority distribution for robotic teleoperation, and it was supervised by Drs. Paolo Rodolfo Giordano and Claudio Pacelito. So this is a brief outline of my presentation today. I'm going to start with an introduction on the topics of teleoperation and shared control. Then I will move to the two main parts of the thesis. The first one is on haptic shared control with human authority, where we design some systems which give some authority to the human user in the teleoperation. We also design in the second part haptic shared control methods with partial human authority, where we give more authority to the autonomous component of the system. And finally, I will end up with some conclusions and future works. So starting with the introduction. Teleoperation was first introduced in the 1940s in order to answer for the needs of the nuclear research. So it allowed the human operator to be able to handle some radioactive material from a safe place. And over time, even though nuclear activities have declined, interest shifted towards other areas, for example, space robotics, medical, and underwater robotics. And even though the telerobotics was first of all motivated in the scenarios where the human operator could not be physically present in the environment because of safety purposes, for example, it was also motivated in the cases where there is limited capabilities for each of the human and the robots in the separately. So for instance, the human is known to have high-level cognitive skills as well as a good scene understanding. On the other hand, the robot has a scalable precision, strength, and repeatability, which could also be exploited. So the idea is to combine these two sets of skills together in order to make the performance of the system better. In a teleoperation system, usually, we have two sides. We have on the master side a device with which the user can control the remote robot, and we have the remote environment where the robot is actually executing the task. So the command goes from the master side to, and on the other hand, we have some feedback which goes from the remote environment to the user at the master level. And this is allowed through a set of actuators and sensors which are present on the both sides. In the design of teleoperation systems, an important goal to achieve is telepresence. So the user should actually feel as if he or she is present in the environment itself. And to do that, usually there are different types of feedback which we can transmit from the remote environment to the user. For instance, feedback has been exploited a lot in the literature. For example, in surgical robotics, like you can see in the Da Vinci robot, which is shown in the figure. We also have haptic feedback, and haptic feedback can be divided into two main categories. We have kinesthetic feedback, which is shown here. This allows to reflect some information about the forces and the positions in the remote environment. And this is usually done through grounded haptic interfaces like the ones shown in the figures. And we also have cutaneous feedback, which focuses more on the local properties of the objects. So it's reflected to the user through some which are in the human. And one way to provide this cutaneous feedback is through wearable haptics in the case of teleoperation. Now, even though direct teleoperation has been used a lot in previous systems, it's often too challenging in itself and tiring for the human on the cognitive level. So, for instance, if we consider the case where we have two manipulators in the remote environment, one manipulator is equipped with a camera and aims to track the objects that we want to grasp, and the other manipulator is commanded by the user in order to go and grasp the object. This scenario is very complicated for the user to be able to control, because the user needs at the same time to control the camera position, and to control the potential collisions between the two robots, for example. So this is why shared control algorithms have started to be developed in the literature, where we share the control of the system between the user and the robot. And in the context of telerobotics, control architectures have classically been divided into three main categories, depending on the level of automation. On one endpoint, we have direct control, this is the simple teleoperation which I have presented before, like the one that was used in nuclear research. On the other endpoint, we have supervisory control. In this case, we give the robot some local autonomy so that the robot can perform the task by itself, while the human only supervises and gives the high-level goal of the system. So this is, for example, how the Mars rover is controlled in space. Because of the time delay between the Earth and space, we need the robot to be able to perform the task on its own, while the human decides on the high-level goal of the system. And in between these two endpoints, we have shared control. So this is where basically the contributions of the thesis lie. And shared control allows the user to be able to be guided during the execution of the task. Now, one way to provide control methods is virtual fixtures, which have been used a lot in shared control systems. And virtual fixtures are defined metaphorically to act like a ruler guiding a pencil in the real world. And there are different types of virtual fixtures. There's also haptic shared control. In this type of shared control, we have haptic guidance, which is given to the user on the master interface. So this way, the user remains in the final control of the remote robot. And haptic shared control has been used in a variety of applications. For example, to guide the human operator towards some position or some path, or even to move the human away from dangerous configurations of the robot. And while we focus in this thesis on manipulators specifically, haptic shared control has also been applied, for example, to control UAVs, mobile robots, and surgical robots. Now, it's also interesting to compare haptic shared control with another type of shared control in the literature, which is mixed initiative control. In haptic shared control, as I have explained, we have here two main components. We have the automation and the human component on the system, and they interact at the level of the master device. And there's also some haptic information which is given to the human in order to guide him or her to perform the task. But in the end, it is the human that remains in the final control of the robot in the remote environment. On the other hand, in mixed initiative control or mixed input control, the human and the automation both intervene in the command of the remote robot through an authority distribution algorithm. And in both types of shared control, the optimal degree of automation versus the human input is not an easy thing to determine. So this is why there are different methods which have been developed in order to either use a fixed or a variable authority allocation scheme. Now, coming to the thesis contributions, first of all, we designed new haptic shared control methods to be applied to robotic grasping and manipulation, which target both the pre-grasp and the post-grasp phases of the task. And we mainly focus in the work on torque effort and human comfort as metrics of interest. We also designed a bilateral teleoperation system with adaptive impedance control for contact tasks. Then we moved to another type of systems with more authority given to the autonomy. So we designed a novel haptic shared technique for robotic cutting, which imposes some constraints motivated by the cutting task. And finally, we also try to use the human experience and the haptic feedback to learn autonomous grasping policies for compliant objects. Now, as a general note, in this thesis, we mainly focused on the design and the implementation of the haptic shared control methods. As such, we did not really address the issue of stability explicitly, but instead we assumed that we have some pacification methods which are implemented in the systems to make them more stable, for example, energy tanks. Now I'm going to start with the first part of the thesis. So in this first contribution, we aim to design a system to minimize the torque effort during robotic telemanipulation. And this work was done in collaboration with the University of Rennes. So the following. Let's suppose that I have a set of objects in the remote, and the goal is to grasp one object and to move it and put it in a box, for example. Then this trajectory for the object is very well defined. It could be, for example, generated using a trajectory planner. It could be done autonomously. On the other hand, the grasping part of the task, even though it could be automated as well, we want the user to be in control of it because we consider that the user has high cognitive skills, which allows him or her to actually know where to grasp the object from. So this is why we want it to be semi-autonomously, the grasping part. Now, the grasping itself is also important for the future consequences of the grasp. So for instance, if I want my object to move along a post-grasp trajectory, which is defined, then if I grasp the object from this side, for example, or from this side, I will be changing the way the robot will move in the future trajectory. And this will impact, of course, the joints and the joint torques on the robot. And the joint torques are particularly interesting for us because in the end, the robot has a limited payload, and we want to increase or maximize the amount of objects that we can manipulate. So this interesting problem has already been tackled in previous work. So the authors in this paper, which was published in IROS 2017, they designed a shared control algorithm to guide the operator towards grasping pose that minimizes the proximity to robot singularities in the future trajectory. And to do that, they designed some force cues which guide the user along the negative gradient of the cost function with respect to the grasping pose. And as you can see here in the figure, they were able to minimize, depending on the trajectory, in the post-grasp trajectory. However, one main limitation in this work is that sometimes the algorithm guided the user towards a grasping pose which is not feasible. So this, for example, grasping pose could be able to minimize the cost function. However, it's not an actually feasible grasping pose. So this is why in this thesis, we extend the previous work, but first of all, we make sure that we design haptic cues which will guide the user towards a feasible grasping pose. We also focus in this thesis on minimizing the torque effort over the future trajectory. So in order to explain the shared control method, we start by dividing the task into three main phases. We have the reach to grasp phase, which is controlled by the human. We have the grasping phase, which is also controlled by the human. The post-grasp phase, which is considered to be autonomous. And our shared control method intervenes in this part, the reach to grasp phase. This is a sample task that we considered. In the reach to grasp, the user operates the haptic device to guide the robot to be able to perform the grasping. And in the post-grasp phase, we consider the robot to be able to autonomously move the object along a designed trajectory. But the problem is that during the reach to grasp, the operator does not have enough intuition about the torques which are exerted on the manipulator in the future trajectory. So this is why in our shared control algorithm, we start first of all by using a grasping algorithm, for example, GraspIt, in order to generate a set of feasible grasps. And then using the pre-planned post-grasp trajectory, which we know for the object, we can calculate for each of these grasps a torque metric, which we will use in order to design the user guidance. And we will be presenting visual guidance as well as haptic guidance. First of all, we're interested in the design of this torque metric. So this task-oriented torque effort function is designed to be the integral over the post-grasp trajectory of the norm of the torques on the robot joints. And in order to calculate this torque, we first of all need the grasp pose. We first need the grasp pose, which is generated through the grasping algorithm. And we also need the robot dynamics, which is augmented by also the object that was by the robot. Of course, here we make an assumption, which is that we already know the mass and the inertia matrix of the object. And this is not always an easy parameter to be able to, that we know. In our experiments, we considered some low velocity tasks. So we were able to compare, if we calculate this torque with and without the acceleration and the velocity parameters, what's the average error between the measured and the calculated joint torques. And we noticed that the average error was quite similar between all these approximations. So this is why in the end, we approximated the calculated torque using only the gravity component. So first of all, we implemented visual feedback for the user, where the user was shown a picture of the object, which is augmented with a set of grasps that we generated. And depending on the color of the grasp, the user knew if it's a good grasp or not. So here, for instance, the lighter colors means a lower value for the cost function. We also designed some haptic feedback for the user. And to design the haptic feedback, we did not just guide the user towards one particular desired position, because this defies the purpose of letting the user be in control of the grasping pose. Instead, we designed this torque feedback as the sum of different components for the different grasps that we generated. And these components would be, of course, proportional to how good the cost function is at this point, and inversely proportional to the distance. So this way, the farther grasps would have a lower weight in the design of the haptic feedback. And the advantage of our algorithm is that it allows us to locally minimize the expected torque. So you can see that the user, for example, could decide to move and grasp the object from the right side or from the left side, and the algorithm will adapt in order to guide the user towards the best local grasp in this case. And we performed a set of experiments in order to test our system, and we compared the results for teleoperation and shared control. So in the case of teleoperation, the user usually goes to grasp the object from an intuitive position, which is usually along of symmetry or the center of the object. On the other hand, with shared control, the user was guided through haptic feedback to be able to perform the task, sometimes from a less intuitive position, but in order to be able to maximize the joint torques over the post-grasp trajectory. We also did a human subject study with 15 participants, and we chose here one object of interest, which was simple to manipulate by the users. And we performed tests with 4 conditions. We had teleoperation, haptic guidance, visual guidance, and the combination of both types of guidance. And we tested the system for 6 different metrics of interest. And the results have shown that, first of all, shared control techniques outperformed standard teleoperation in most of the metrics. We also showed that the haptic guidance performed better than the visual guidance, but it was the combination of both types of guidance which led to the best overall results for the users. And this agreed with the subjective study. So 13 subjects out of 15 found the combination of both types of feedback to be the most effective in completing the task. Now, in the next solution, focus more on the user comfort in robotic telemanipulation. And this work was done in collaboration with the Universities of Pisa, Siena, and IIT in Italy. And the idea behind this work is that usually shared control methods do not really focus on the user comfort, even though this is a relevant issue because sometimes the user needs to do the task over and over again, and it could get physically tiring. And some examples exist on this work in human-robot interaction, but not in teleoperation applications. So the idea of the system is to start by designing a ruler estimation metric. Then using the inverse kinematics of the human arm, we can calculate the user workload online. Using this workload information and some information that we have about the task at hand, we can generate haptic active constraints that will guide the user towards performing the task, but at the same time while optimizing the physical workload required. So to do that, we start by designing the workload parameterization. And for this, we were inspired from the Rula metric, which is commonly used in ergonomics to estimate the risk of a certain pose of the user. And usually, the Rula metric uses information from the trunk, the neck, and the upper limbs. But we chose to focus on the upper limbs because it's the part of the body that is most used in the teleoperation. And the way Rula works is through a table where we have scores given to each angles of the human arm. And in the end, we get a final score in order to assess the risk of the posture. But the problem with Rula is that it is discrete and it does not depend on the exact angles of the arm. So instead, we designed a continuous function, which is inspired from Rula, to quantify the effort exerted by the user. And to do that, we started by modeling the human arm using a spherical joint for the shoulder, a spherical joint for the wrist, and a revolute joint for the elbow. And we calculated the workload to be the sum of the squared distances between each angle and its resting pose. And here you can see an example of a comfortable pose where we have a low value of W. And on the right, you have a less comfortable pose with a higher value of W. And of course, here we assume that we already know the angles of the arm, which is not an easy thing to do because the arm is assumed to be 7 degrees of freedom arm. So it's redundant. And so we design also an inverse kinematics algorithm where we introduce an arm angle, which is this angle of the elbow that we call psi. And using this angle, we can resolve the redundancy and calculate the other angles of the arm. This is the teleoperation that we use in our scenario. So we have on the master side the virtuoso haptic interface, and on the remote environment we have the Panda Franca, the Franca robot Panda, and we design the control of the robot to be in velocity, while on the master side we are interested in the design of this haptic feedback that will guide the user to perform the task while minimizing the physical workload required. So this FM haptic feedback is designed to be the sum of a weighted of 2 components, which are weighted according to 2 weights, alpha and beta. The first one is FW, which minimizes the workload, and the second one, FR, is related to the robot, a robot cost function or a task-related cost function, which could be anything. But in this particular scenario, we chose the cost function to be the distance to the target because it was a simple cost function to implement. And we show here a representative example where the task was to move the robot from a point A to a point B, which are on the same height. So as you can see, when alpha is equal to 0, we have no human component, and the user is guided along a straight line because it's the fastest way to go from one point to the other. As we start increasing alpha to 0.2, for example, we start accounting more for the user comfort, and the user is guided towards a more curved path in order to minimize or optimize the user effort during the task. And finally, if alpha is equal to 0.4, we also significantly account for the user comfort, so the user is also guided towards a more curved path, again, to execute the task. And we also did a user study in this case where the task was a pick and place task. So we asked the user to move the object from one point to the other. And we tested the system for 3 different objects, 2 poses per object, and 3 weighting conditions that I already presented. And the results have shown that we had an improved user comfort as measured by the NASA TLX test data, in addition to the cost function that we presented. But this came at the slight decrease in the performance in terms of completion time and placing error. Now, finally, I present a system, a variable impedance control system for contact tasks. Now, this part was not included in the thesis manuscript because it was completed after I submitted my manuscript, but I added it here for completion. And this work was done in collaboration with Professor Lee's lab in TUM during my short visit. The idea behind this work is that humans are skillfully able to interact with the environment by modulating their force and their stiffness. So several works in the literature try to extend this capability to teleoperation systems using variable impedance control. And usually to do that, they either use some grip force sensor or EMG data, or even a joystick-like device where the user can manually input the desired stiffness of the system. The main idea behind our contribution is to be able to do that, but in a system where we automatically estimate the user stiffness. So to do that, we start by learning from human demonstrations, and then we keep the stiffness of the system low, and we adapt it accordingly by checking the interaction with the environment. So compared to a constant high stiffness, we try to mitigate the effect of the induced master motion. On the other hand, as compared with the constant low stiffness, we achieve better tracking accuracy. This is our system architecture. So we had two main blocks in the system. We had the learning block and the reproduction, or the teleoperation block. In the learning phase, we start with some user demonstrations where we record the position, velocity, acceleration, and external force components. And then using an interaction model, we can estimate the stiffness desired for the robot. And this set of forces and stiffness parameters is inputted into a Gaussian mixture model where we can get the relationship between the two. And finally, the GMR allows us to compute for every external force vector that is measured on the robot in real time, a desired stiffness parameter that we will use in the teleoperation. So this KT parameter is input to the robot controller that you see here. And on the master side, we also have the external forces which are provided to the user through haptic feedback. In order to test the system, we chose a cutting task. And for the learning, we started by doing some teleoperated cutting tasks on 4 different materials with different properties. And we did 5 demonstrations for each material. And we started by testing our system versus 2 standard conditions, a constant low stiffness and a constant high stiffness. And we did that on a material which was not used in the demonstration phase. And the results showed that, first of all, in terms of completion time, our approach came close to the high stiffness approach, but it outperformed the low stiffness case. On the other hand, in terms of smoothness, which was measured by the jerk force and the jerk motion, we were able to get results which are better than the constant high stiffness. We also tested the system in a case where we had a communication delay of 20 milliseconds, and we did that by comparing the system to a constant high stiffness. And as expected, with the constant high stiffness, the system had a lot of oscillations in terms of the force and the position, and the user was not able to complete the task. On the other hand, the variable impedance controller was able to modulate the stiffness of the system in order to be able to the user execute the task. And finally, the final experiment that we did is by comparing our approach to a baseline condition with constant low stiffness for teleoperated cutting. And here we had 2 different materials that needs to be cut. So using constant stiffness, you can see that the tracking error will change. On the other hand, for the variable stiffness, once we move from one material to the other, the stiffness of the system regulates itself, and we are able to achieve a good tracking error, or almost constant, over the experiment. Now I get to the second part of the thesis, where we try to give more weight in the system to the autonomy component. And the first application that we targeted was robotic cutting. Robotic cutting is a relevant task because it is included in many applications, such as surgical robotics, manufacturing, and waste management. And it's particularly interesting for shared control because it requires high dexterity level, and it can have some serious implications if it fails. And cutting in particular has a variety of constraints that needs to be done. So we have to make sure that there is no lateral motion which is done while we perform the cutting task, not to ruin the material. And also we should do no rotation in place to be sure also that we do not ruin neither the material nor the cutting tool itself. So this is why shared control architectures have been proposed in the literature to be able to tackle the different cutting tasks. One example is the work of Rahaf Rahal, where they introduced non-holonomic constraints in the cutting task, and their task was to cut a straight line in insulating foam. And they consider 4 different modes in their system, but the main limitations of this work is that, first of all, we had no constraints which are reflected on the master interface, and they also considered a simple task of cutting a straight line. They also focus in their work mainly on time delays, which are not present in our system. So the methods that we present are 3. We start with a simple teleoperation, denoted by T. It's a simple teleoperation, but we include it because it's still used in a lot of applications. We had a unicycle approach, denoted by U, and the car-like approach, denoted by C. And I will be explaining them later on. And in all of these three modes, we make sure that the master and the robot are allowed to only rotate around the z-axis, so they are constrained in the plane, and we let the three translation directions free. The user also receives two types of haptic feedback. We have the contact forces from the environment, and we have the non-holonomic constraints that we add. So starting with a simple teleoperation. In this case, we let the user be in control of the three planar degrees of freedom and the vertical direction, what the remaining degrees of freedom are blocked. In terms of robot control, we have a Cartesian impedance controller here. And on the master side, as I have explained, we have two types of feedback. We have tau c, which is the constraint force, the non-holonomic constraint. And in this to 0 because it's a simple teleoperation. And we have tau nc, which is the non-constraint force, which is reflected from the remote environment. And also in this case, it's along all the directions. And you can see in the video how the system performs on the master side. So the user is able to move in the plane, both in translation and in rotation. And the user is also free to move in the vertical direction up and down. In the unicycle approach, we try to add a constraint, which is that no lateral motion should be done. And to do that, we enforce this constraint on the master and on the remote environment. So the scalpel is constrained to move only along two translation directions, which is the cutting direction and the vertical direction. And the master is also blocked through haptic feedback to enforce this constraint as well. And here you can see also on the master device, so the user can rotate in the plane, can also move along the cutting direction, and move in the vertical direction as well. However, the lateral forces are blocked. And this constraint also rotates with the user as the user rotates. In the car-like approach, we add to the previous condition another condition, which is that also we should not be able to do any sharp motion or in rotation or any rotation in place. And to design the system, we were inspired from the way a car works. So when you're driving a car, you start by rotating the steering wheel, and then it's once you start hitting the gas pedal that the car starts moving and starts rotating in practice. So here we did almost the same. So we had the master orientation, which was mapped to a desired radius of curvature on the level of the remote environment. And then this rotation of the slave was commanded depending on the radius of curvature desired, but also on the forward velocity of the master interface. And in order to let the user feel... Yeah. Where's the problem? Weird.
Yes, we try to take care of the slides.
You cannot see them. Should I share them from my PC?
Yes, now we are back.
Okay,
Yes.
I won't change anything.
Yeah.
Okay, cool. Yeah, so as I was saying, we're in the car-like approach. So you can see in the video how this is implemented. So we have, first of all, the same constraint as before, the non-holonomic constraint. And here we added a spring to let the user feel what's the current orientation of the slave robot. And the user is also able to move along the cutting direction. Lateral motion is blocked as well, similarly to the unicycle mode. Now we performed a set of experiments with 12 participants, and we had tested the three conditions for three different...
We lose the slides.
Lost again? Okay.
Yeah.
Maybe I can remove it from here and just share my screen from the laptop. It's better. Can you see it now?
Yes.
Yes, it's okay. Thank you.
Good. Okay, so you can watch. Okay, so yeah, we tested the system for three trajectories that we chose, which were of different difficulty, and they were inspired from surgical incisions. So we had a straight line, a bent line, and a sinusoidal shape. And this is a representative example of the task. So we have the user, which was asked to cut the sinusoidal shape in this case. So we start by drawing the target shape on the material that we want to cut without ruining the material. And then the user is asked to perform the cutting in the fastest way possible and as accurately as possible. And this is a representative trial using the mode of the unicycle. So the user is able to cut and at the same time receives feedback about the lateral constraints and also about the force reflected from the robot in the direction of the cutting task. Now, concerning the results, we started by testing different metrics. So we had 6 metrics that we considered, 5 metrics. So we have the completion time, the error in carving the target shape, the maximum and the mean lateral forces, as well as the roughness of the cut. And we mean by roughness how clean the cut is from any oscillations or bends. So to calculate it, we took the average distance between the trajectory that the user cut and a filtered trajectory, which was calculated from this initial one. And the results showed that the unicycle approach performed better than teleoperation in most of the metrics, and the car-like approach also performed better than teleoperation and better than the unicycle approach. So overall, in terms of objective metrics, it was the car-like approach that performed better. And this, however, did not agree with the subjective results, because 8 participants out of the 12 found the condition of the unicycle to be the most effective, and only 1 participant preferred the car-like condition. Now, an extension is also in progress here. So we're trying to design a shared control method for robotic teleoperation, where we use the previous system to design a guidance algorithm for cutting tasks. So the idea is to design a mixed input shared control, where we adaptively change the authority allocation in the system based on the confidence of the performance for each of the human user and the autonomous components. And we also, ideally, we would like to teach novice users to perform a task based on some user experiments. We started by designing this new metric to assess the user performance. We also designed the shared control method that changes the authority allocation online based on the user confidence metric. And finally, we also designed some haptic feedback that allows the user to feel the environment and direction of cutting, while also receiving some information about how the authority is being distributed. So to do that, we added on the unicycle mode, which was presented before. So we have the first 2 components, which reflect the user command along the cutting direction. So the user is still in control of the forward motion. We also have the non-holonomic constraints, similarly to the unicycle mode from before. But here we have the 2 components for the guidance system, which is along the orientation along the Z direction. So we have tau T, which is the teleoperation torque around Z. And we have tau A, which is the autonomous torque around the Z components, which are weighted according to an alpha weight. To design this autonomous part, we used a unicycle path following control problem, and we are interested mainly in the design of this alpha parameter in order to distribute the authority. So to design alpha, we start by using expert user demonstrations. So we learn the desired trajectory in the X and the Y directions. And then we are able to compute online the confidence metric for the robot, which is dependent on the covariance matrix from the learned data. And we also can compute the confidence metric for the human operator. And the idea behind the confidence metric is to be able to know how well the user is performing. So the farthest the user is from the trajectory desired, the worse his or her performance is. So this is why we use the Mahalanobis distance as a metric, and we averaged it over time in order also to get the time effect on the system. And we designed the authority allocation parameter alpha as shown here. So the idea behind it is to be able to compare the 2 confidence metrics. If the 2 are equal, then we want an alpha of 0.5. This way, both inputs intervene at the same time in the system. When the robot confidence is the human confidence is low, we want alpha to be equals to 1, so the system needs to be mostly autonomous. On the other hand, when the human confidence is higher than the robot one, we want alpha to go to 0 and to give more control to the user. And we also designed some haptic feedback. So we have contact forces along the cutting direction. And we also had the orientation of the master mapped to that of the remote robot so that the user can have an idea about the authority allocation scheme. And finally, we did some preliminary results. So in the first row, we show a trajectory where the user starts close to the trajectory. So we had a high human confidence at the beginning. And the second row, we had a trajectory where the user starts away. So we had a lower human confidence. And in both cases, we have the robot confidence, which is similar because it mainly depends on the learned data and not on the actual performance of the user. On the other hand, the human confidence varied. So here we have a human confidence of around 0.5, and here it's around 0.25. So this intervenes in the changing of the authority allocation based on the user performance online. Now, on the final contribution, we try to use a learning from demonstration, and which uses information from the haptic feedback and user interaction to be able to train an autonomous grasping algorithm. And this work was done in collaboration with Syntef. So the idea behind this is that research into compliant objects such as food is gaining a lot of importance nowadays. And it's currently a field which is predominated by human labor, which is sometimes very tiring and repetitive. And even though there are some learning policies which exist in order to make this grasping autonomous, usually these policies lack direct haptic feedback. So the user has no idea about the exact amount of force that's applied on the environment. So While these forces are very important because in the case of compliant objects, we don't want to actually degrade the quality of the produce. So we designed a learning from demonstration approach for teaching autonomous robots to perform this grasping action. And we want our system to be human-centered because we want to learn how humans grasp. And we also want it to be haptic-based because we want to use this haptic force in order to know exactly how much force to apply on the object. And so we started by asking 5 different operators to perform a grasping action barehanded, and we recorded the contact area between the user's hand and the object. So we used some paint and machine vision to do that. And this allowed us to generate a heat map of this contact area between the user hand and the object. But of course, this was not enough to design an actual autonomous algorithm, because in the end, when we apply this to the robot, we will have less dexterity than in the case where the human is barehanded. So we added also some data from haptic teleoperation of an expert. To do that, we used a system where we augmented the haptic interface with a haptic glove. And this glove has 3 fingers to manipulate the robotic hand, which also has 3 fingers. And it allows us to get some haptic feedback. So this is the system that we designed. We have at the same time the position of the master, which is mapped to the remote environment in terms of the robot position, but as well as the finger positions. And we also have some haptic feedback, which goes from the fingers of the robotic hand to the finger of the gloves. And then we designed the learning policy. So we used SVR to do that. And we used both data from the direct interaction and the teleoperation in order to do this design of the algorithm. And we used the different types of information, such as the position and orientation of the robot, the position of the fingers, as well as the tactile information from the sensors in the robotic hand. And we devised 4 different learning algorithms. And the first one, it was a simple SVR, where we used all the data which were normalized with the same weight to input to our algorithm. We also designed a weighted SVR, where we weighted the different parameters by experience to maximize the success rate of the grasping. And we also designed an algorithm where we weighted the tactile information from the robotic hand using the heat maps that we got from the human demonstrations. And the final one is similar to the weighted with heat maps, but we also add the time component and the temporal variation. We also had 3 control conditions. So we had a recent state-of-the-art technique which was implemented. And this technique, we had the user perform some teleoperation demonstrations to teach the system, but the teleoperation was done using a non-haptic joystick. So the user had no haptic feedback. And we also had 2 simple impedance controllers, one with a gentle force threshold and the other one with a strong force threshold. So the hand was asked to close on the object until a certain average threshold force was reached. And then we ran the experiment for the autonomous grasping. So you can see for the different objects, we performed 30 grasping trials, and the system was able to autonomously grasp the objects that we trained the system on. Now here, this table summarizes the results that we got. So first of all, we started by comparing the different SVR methods that we present. And as you can see, for the objects that we used in the demonstration phase, we had the highest success rate for the SVR, which was weighted with the heat map values, both with the temporal and without the temporal variation. On the other hand, when we added 2 objects with the smallest size than the ones used in the learning, we get the same amount of success. And we also did some adaptability trials where we tried to use some objects to train the algorithm here, but then we tested the algorithm on the other objects of interest. And the results have shown that if we train the data with for example, the aubergine values, and the aubergine is quite heavy, then we are able to grasp all the other objects. On the other hand, if we train it on the lettuce, which is less heavy, then we were not able to grasp because we were not supplying the right amount of forces to be able to grasp the other objects. Now I come to the last part. So in this thesis, we presented multiple shared control architectures that utilize haptic feedback to convey information to the user, but also to interact with him or her. And these different results showed, first of all, the advantage of shared control versus standard teleoperation, because teleoperation is, in many cases, is too cognitively demanding or even physically tiring for the operator. And we also presented new ways to divide the authority between the human and the automation system to be able to perform different tasks, such as grasping, manipulation, and robotic cutting. And so we presented systems with high human authority and with low human authority. Now, as a conclusion, we started by presenting 3 systems on shared control methods for robotic teleoperation. So we have in the first system soft constraints that are implemented. We focused on the task execution, and the system proved the success of shared control versus standard teleoperation. In the second system, we also implement soft constraints, but we focus, in addition to the task execution, on the user comfort. And even though the shared control was improved the results in terms of user comfort, there was a slight decrease in the task execution. And in the final work here, we also had soft and hard constraints. We focused on the task execution, and the shared control performed better than simple teleoperation, but it was hardly perceived by our subjects. We also presented two systems where we combined teleoperation with learning from demonstrations. And the first system was more designed towards improving the quality of the teleoperation, while in the second one, the goal was to improve the automation in itself. And these results raise many different interesting points from different perspectives. And the first question that we can ask is, who should be the ultimate decision maker in a robotic system? Is it the human or is it the robot? And what is the desired strength of haptic feedback that we should apply, or authority allocation, so that the user can actually follow the desired recommendation from this automation, but at the same time does not feel like he is out of control? And the second question that we can ask is it possible to optimize at the same time the human comfort and the robot-related parameters, or is it always a compromise that should be done between the two? And finally, in terms of future work, I think there are many discussion points which could lead to future work. One of them is the nature of the feedback provided to the user, not only in terms of visual versus haptic feedback, but also in terms of the haptic feedback itself. So in my thesis, I focused on kinesthetic feedback, but it would be also interesting to combine this with some cutaneous feedback, for example, using wearable haptics. For instance, it would be important in the case where I would like to give the user different information from the task-related component, for example, and the human comfort component. If I decouple them, the user would be able to see which side of the system this feedback is coming from. And it would also allow the user to perform the task while not being hindered in the control if we provide this information using a wearable haptic device. And the second point for future work could be also the study of virtual fixtures and shared control methods. Where should we apply these virtual fixtures? So if we apply them on the master device like we did in our case, it would increase the stability of the system. On the other hand, in some cases where we want to exactly perform the task on the slave side, then it could also be interesting to use the slave information in order to design these virtual fixtures. Thank you for listening. This is a list of my publications, and I'd be happy to take any questions.
Thank you, Rahaf Rahal, for this very nice presentation. So now we will switch to the session of question and discussion. So traditionally, in France, we start with the reviewers and we consider a criterion of distance. So I think that we can begin with Professor Paolo Rocco for the question, then Stéphane.
Okay, thank you. And first of all, I would like to congratulate with our speaker and the author of this dissertation. I read it. I mean, it was a very pleasant reading of your thesis, and I tried to write, I mean, in my report, some suggestions that were intended just to further improve your work. So maybe the most important point I would like to raise, and I would like to see your opinion, is something that I already mentioned in my report, is about the fact that in your thesis, the issue of stability of all this system is not, I mean, addressed in much detail. Was this a choice? I mean, for example, the issues related to delays in communication and so on. Is this a choice that you made on purpose, or I mean, can you comment a little bit on that?
Yes, so actually this was a choice because in this I was mainly interested in the design of the shared control methods and the design of the haptic feedback and the interaction with the user, not on the stability itself. Now, in most of the algorithms also, in all of the cases, we did not have any significant time delays, so the system was stable in all of the systems. We did not have to target this issue. In the case of the cutting, I think I also mentioned it in the manuscript that it could also be nice to do some stability analysis because we had a lot of feedback from the environment and the system was torque controlled. So I think it could be nice to do some stability analysis, but in terms, it was not really included in the thesis because it was not the main goal of the thesis. So here we were more interested as a choice to work on the haptic feedback and the design of the shared control method, not on the stability. But most in the works, we can include some stability control method, like many pacification algorithms exist, like energy tanks, for example, and we can include them on top of the existing system in order to improve the stability.
Yeah, I think that it would be a nice, way to proceed, in your research, because now you have this nice framework for classifying and studying and implementing these shared control principles. But then, of course, you need to be sure, or to guarantee some form of stability and robustness of this stability. So I really encourage you to also move in future research also to this part of your research. So coming to another point that I raised in my report about intuitiveness of some of the choices that you made. So, for example, the first part where you actually based the feedback, maybe I'm simplifying a little bit, but the feedback to the human operator based on the future in order to make easy the work of the robot after the grasping. So, and I understand that the method works, but I just wanted to know from you, to hear from you, if the user is actually aware of the fact that the robot, the system, is guiding him or her towards, the satisfaction of a task, a robotic task that is going to happen later, so to say. Is this something that makes the user comfortable, or what is the acceptability from the user point of view of this method?
Yes, so as you said, so we target a task where the first part is performed by the human, which is the grasping task. It's a semi-autonomous control system. And then the final trajectory is performed autonomously because it could be designed using some trajectory planning algorithms. Now, in terms of the user perceivedness, actually in our experiments, when we compared the different methods, so we had the simple teleoperation where the user was given the freedom to grasp from any point. And then we had the different shared control algorithms. We also told the user in the teleoperation case that the goal of the system is in the end to minimize the joint torques in the future trajectory. So the user was aware that the system is targeted towards improving the trajectory of the robot in the future task, and not only to make it better, but also sometimes to make it feasible, because in the end, if the object is grasped from a wrong position, then the future trajectory could not be feasible because it could incur, for example, high load on the joints. So the user was aware of this, and it was intuitive for the user to understand the goal of the system. So the user accepted that, okay, I'm grasping it, but I should have in mind that in the end, I want to minimize the joint torques on the future trajectory. And we did not see any problems in the acceptance from the side of the users.
But the user was aware, of that. So
Yes.
that the system was actually guiding him toward this. Okay, that's important.
Yes.
And again, about intuitiveness, I was a little bit, how can I say, wondering whether, the visual feedback, I make reference to the picture where you have all this green and then red, arrows or similar to that. And that is supposed to guide the user towards a better kind of grasping. Can you again comment a little bit on if the user is actually able to figure out from that picture the way, a suggestion to perform in a better way, this task of kind of teleoperation? Is this something is that picture something from which the user can easily extract usable information?
Yes, so the visual feedback was very simple. It was, as you can see in the picture, just the picture of the object with the grasps. And we also added the robot in order for the user to see how the object is oriented in space. And in the beginning, before the experiment, we allowed the user to be able to check the different grasping poses, their color. We explained how the color relates to how good the grasp is. And we allowed the user also to rotate this scene in 3D to be able to see the object from different angles and to decide on where to grasp the object from before starting the task. Now, this was done offline because in all cases, the grasps are generated offline. So the grasps do not change over time. There was no real reason to add an autonomous visualization of the object. Now, I think also a better way maybe to provide this would be in the future to make it in real time and to just show the user, for example, the best grasping poses in the local neighborhood of where the user is trying to grasp. So this could be one possible idea for the future to make this better or more intuitive for the user.
Yeah, that's maybe would be a great idea. I mean, to restrict, I mean, the option that the user has to consider, maybe to ease, I mean, his cognitive load. During your presentation, you mentioned the assumption of the knowledge of the payload, if I'm not wrong, in some of your methods. Wouldn't this be, first of all, what kind of knowledge do you need? I mean, is it just a geometrical knowledge of the payload, or also you need something about its inertial properties? And second, how do you rate this as an important assumption, and whether it can be overcome with some form of robustness of your method that might be kind of work irrespectively of the payload that it picks?
Yes, so the algorithm needs the payload, and we also need, in addition to the mass, we also need the inertia matrix, which I have said also sometimes this is a limitation because it's not always available. Now, in the particular case where we had low velocity tasks, as I explained, we could use only the gravity information of the object to approximate the calculated torque, and this could help us a little bit by not using the inertia matrix, but we still need the geometric properties of the object, and we still need the mass of the object. So this is, of course, not ideal, and in an actual situation where we don't have access to the object itself, we would need some estimation parameters for the mass of the object to be able to perform the algorithm.
Okay, and then moving to the method where you actually account for the ergonomics of the human arm. You mentioned the ruler method. I mean, that's fine. It's one of the methods that is used. Maybe it's not the only one, but of course you can stick with that. And from that you derived a cost function that you call W. That at the end, I mean, is quite simple. I mean, it's just the distance of the joint variable from 0, basically, and maybe 1 from pi half. I mean, the process from the ruler method to that cost function, don't you, maybe you have made some oversimplification or not? I mean, is a straightforward consequence of the ruler method that the cost function is just kept the joint angles close to 0?
Yes, so actually it was not a simplification, but more an intuition. So we use the intuition behind the ruler. So in the ruler, if your arm is at 0, then yes, you have a score of 0 if the angle is at the resting pose in the table. And then eventually you start adding the different angles. So this is why we also added in the cost function the different angles contribution to the workload. But I think the difference is that in the table of the ruler, you have the score which is given. So it would not matter if your angle is at 0 or is it at 20. It would consider the same score in the table. So this would create a discrete form of the metric. So we just tried to make it more continuous, but we still followed the intuition behind the ruler metric.
Okay, and yeah, maybe you should remember from reading the thesis and also from your presentation, but now, so how do you actually compute, I mean, the angles of the human arm? Are you using some feedback, visual feedback? I can't remember.
So what we did is we assumed that the shoulder is fixed for the user, and we had the position of the wrist from the position of the master interface.
Okay.
And then we used the parameterization angle, which is this elbow angle. Using this parameter, which is the elbow angle, we were able to express all the other angles. So in order to compute the inverse kinematics, we started by taking a range of this angle that we introduced, a feasible range for the human arm. We calculated for each the different angles of the human arm, the corresponding angles, and then we chose the one, so the elbow angle, which generates the configuration of the arm, which would lead to the best workload value. And here we made an assumption that the user would choose the elbow value, which would decrease the human comfort, so by naturally.
Okay, and yeah, maybe the very last question. In the last chapter, as I mentioned also in my report, it's basically a completely autonomous task from the robot. So you introduce it in the framework of shared autonomy, but I mean the link with the human is kind of indirect in this case. Would you comment a little bit on that? Do you think that this piece of work that, I mean, by the way, I think that is quite interesting, fits well in the overall picture of shared autonomy, maybe to the extreme of the, I mean, the robot autonomy, I guess. Can you comment a little bit?
Yes, so I agree that this work is not very similar to the other works in terms of really fitting into shared control. But since in the thesis we presented different systems with a variable authority given to the human versus the autonomy, this final work, even though it is the final goal is autonomy, so make the robot autonomous, it's used some information from the teleoperation and also from the way a human grasps. So in the end, we use this teleoperation data to guide the robot. So in some way, as you said, it is implicitly including the human input. So this is why we put it, maybe as you said, it's on the extreme end of the spectrum of shared control. So it's really applied to autonomy, but uses some human information, which is why we also included it under this term.
Okay, good. And so I think that for now, I mean, I'm satisfied. Maybe if more question will come from also listening to the other question, I will, if you allow me, I will ask more questions later. Thank you.
Of course. Thank you. Now we give the floor to Professor Stéphane Régnier.
Thank you very much. You are hearing me? Perfect. I would like to thank the supervisor of the thesis for the invitation. The work is excellent. I can start by that. I would like to congratulate Rahaf for the presentation, which was very, very nice and clearly explaining the work and the contribution of the thesis. I am really impressed by the number of collaboration, also by the number of papers, as you mentioned here. It's really very impressed. The goal of the thesis, it was to propose not only method, but maybe schemes to improve the quality of some tasks and for manipulation, cutting, exploiting haptic as a means to provide contact force to the user and also guiding the user and also training part, which is also interesting, and you had this discussion. Few words about the thesis. Very clear. I enjoyed the reading, clearly written, well explained, state of the art. I think it's very important also to mention. The presentation today, 78 slides. It's again, very impressive. Now I will come back to the thesis and to the slide. Maybe, and sometime I will re-ask maybe the same question just to clarify, because you were very, very quick. So sometime maybe I will ask some questions to better understand how you tune the game, for example, how to define the scheme or things like that. So first of all, starting slide number 15.
Yes.
Maybe we will. I will ask some question about the slide. It will help.
Yeah, so you can see the slides, right?
Yes.
Okay. 15.
Yes.
Yeah.
Okay. So the question I have, it's a general question, even also asked by Paolo, but the idea to minimizing the torque, to minimize the torque, to increase the number of objects you can manipulate. I am not really convinced by that. Can you explain why it's so important and how you can see as a solution for increasing the manipulation and the post-graph trajectory?
Yeah, so in terms of, so to visualize maybe the problem, if we consider, for example, a nuclear environment where we have different objects, sometimes the user needs to perform a lot of tasks in teleoperation. So the user needs to grasp the object and then move it around, and this is quite tiring. So what you propose here is a system where this moving of the object is done autonomously because the trajectory can be easily generated. But we only allow the human to perform the first part, which is the grasping itself. But we cannot allow the human to just grasp the object from any side, because if we grasp the object from one side, maybe the post-grasp trajectory that is planned by our algorithm will not be executable. So it could generate high torques, for example. So we consider torques, but this could also be propagated to any other metric. So this is why it's important to allow the user to have a feeling of where he should grasp the object from. Because if we just let the user choose the grasping pose, even though the user has the cognitive skills and can choose a good grasping pose for the object, sometimes it's hard for the user to imagine what kind of joint torques will be incurred on the robot in the post-grasp task. So this is why we designed this shared control algorithm.
Okay, but you think by minimizing and by your function, you will answer to this question.
Of minimizing the torque?
Yes, for the post-torque, yeah. Because
yes, sorry, go ahead.
No, but just to be sure. Okay, so by just how you be sure that minimizing the torque will again, you will be sure for the post-grasp trajectory. It's not clear in my head.
I will be sure that it's feasible. So in terms of torques,
yes,
it's not sure it is feasible. So to make sure it is completely feasible, we need to compare with the joint limits of the angles. Okay. So for now, it is just about minimizing the joint torques in the end and the post-grasp trajectory. But this metric could be changed.
No, yes, no, I mean, just to understand. Okay, so okay, I understand now. Slide number 19, please.
Yes.
Just after, yeah. So, okay, I understand. So you finally, at the end, what you have demonstrated is you neglect a part of the object dynamics. So it's clear the demonstration is, but you didn't give us an analysis of that. Can you explain a little bit why finally it's not so important, the dynamic of the system?
Yes, of course, it's important in the cases where you have high velocities, because then the inertia would roll. But in our case, yeah. So in our case, we had low velocities, which is why the components of the inertia and the Coriolis terms were quite negligible into estimating the torques.
Of course, but it's not related to the fact that you are on low velocity. It's very simple. You can use only a kinematic model because you have selected low velocity, finally, the conclusion, no?
Sorry, I could not,
no,
I didn't really understand.
Yeah, the question is, you explain you can define the object and the dynamic of the object by the equation with the dynamic of the system, but finally you use low velocity of your system. So finally, it's only due to the fact that you use low velocity, you can neglect the dynamic of the system. No?
Yes, so in the beginning, we tried with all the components together.
Yes.
To make sure that we are estimating the torque correctly, for sure. So in the beginning, we included this. But since this needs also the estimation of the inertia matrix, for the experiment, we just dropped these two terms because it was low velocities and we could ignore.
It's clear. Okay. But it's for low velocity for my. Okay.
Yeah.
Slide number 24, please. In every part of your thesis, you have a lot of experiment carried out with subjects, and it's not very easy to follow the result of that. You can imagine here, for my side, in 1 minute, reading this slide, and very often what we find at the end, at the conclusion of this part, is 12 subjects among 15 or 13 subjects of 15 or things like that. And finally, what are the contribution of this? What we can have? What kind of information we can obtain of this kind of analysis?
Yes, so you're talking about this particular work, or you mean in general?
In general, it was just an example, because even in the thesis, the reading of that part, it was for me, for my side, the most difficult part, just to extract result. And it's very often in this case in aptitude feedback when you perform and task with end user, because you have to select, you have a lot of experiment and a lot of hypotheses which have to be done, and things like that. So even at the end here, even it's promising, the real analysis is not so easy. And finally, my question is how deep we can, how deep this kind of analysis can be useful for aptitude user.
Yes, so when in our different experiments, we had different metrics. And of course, the conclusion sometimes was, we want to prove if shared control performs better than simple teleoperation. So this could be really, yes, the general conclusion to do. But because we have some user tests with a lot of people, a lot of participants, we wanted to make sure also that the different metrics that we consider have some statistically, some differences between them that are statistically significant. So this is why we had to include this statistical analysis also to make sure, so which metrics do play a role in differentiating between, for example, shared control and teleoperation, and which metrics do not really show any significant difference. So sometimes just looking at the mean value is not significant enough.
I know it's very difficult on micro teleoperation. I have tried several times to carry out this kind of experiment, and the result is not so obvious to be clear. And so it's why I wanted your opinion about that. Yes, we have several cuts during the slide number 29 and 30. And I think if we can show them again.
Yes, of course.
So it's yes, and can you re-explain how you evaluate this? I have understood that the idea of the workload parameterization was to have a formulation of the workload, but it's unclear how you define this W for my side.
Yes, so here we have the human arm, which we modeled by 7 different angles. So we have here a spherical joint, the shoulder, a spherical joint at the wrist, and this elbow angle. And for each angle, we have a resting pose angle. So if you look back at this ruler table here, when the angle, for example, of the shoulder is 0, then we have a low score, while when the angle increases, we have a high score. So we try to add this in the continuous estimation. So for the elbow, the resting pose is pi/2. So this is the best pose for the human arm. While for the other angles, it is 0. So this is why it's just the weighted sum, the sum of the squares of each angle minus the 0 value or the resting value.
Okay. And just the next slide, please.
Yes.
So we haven't. No, it's not the movie. Sometimes there is a movie and I didn't see the movie. Sorry. Yes.
Yeah.
And the question, it's unclear for my side how I have understood how you tune alpha and beta. Okay, it's empirical, or you have a method to tune the gain.
Yes. So for alpha and beta, it's not. There's no method for now. So what we did is, for the case of alpha is equal to 0, it's clear. We want no human comfort included in the cost function. Now, as we start increasing alpha, so here we took values of alpha is equal to 0.2 and 0.4. We always wanted alpha to be less than 0.5. So this was one first intuition, because if alpha is more than 0.5, then the comfort component in the force feedback would be higher than that of the task, and the user would not be able to execute the task. So the user will not have information enough to go grasp the object. So the value of alpha should be less than 0.5 in our design. We only chose 0.2 and 0.4 as representative examples. In the end, it could be tuned based on what kind of task we want to do and how much weight we want to give for the human comfort versus the task itself.
Okay, so it's clear, yeah. And what is your idea about to tune these games? Do you think we can have an automatic method, or for the people, I don't know, because if you have to select and to tune them for every experiment, it will be it could be a difficulty.
I agree that it would be nice to be able to tune it automatically. One way I could think of is, for example, to do it through some learning. So if we do, we take different values of alpha, then we try to check if we are able to do the task and if the human comfort is improved, and try to find this optimal value of alpha. It would be nice for the task, for example.
Okay, slide number 43. So I see nothing about the end user experiment. Can you?
I don't know if I have a picture.
No,
so
don't worry. But it's again very difficult to see any conclusion about that. And your conclusion, of course, are well explained, but it's only two cases, high stiffness and low stiffness. And in between, there is it's very difficult to see on the result.
Yes.
I am very. I really enjoyed the analogy and the use of non-alarmic constraints. It's a very good idea, I think. I really enjoy that. Maybe you mentioned it was not the first time, but I was not aware of that. But really, it's very impressive. The idea is very good, I think. And can you show us the slide number 49? Okay. Yes. Okay. So the question is about because I haven't seen the movie. So here you demonstrate the force feedbacks and the constraint.
It's a video.
Yeah. What is it? Can you re-explain the master side? What are the force feedbacks and the non-alarmic constraint of the system?
Yes. So in this case of teleoperation, we have no constraints. So here in the video, we only show that the user is free to move in the plane.
Okay.
Of course, he is blocked, so the user should remain in the plane. There's no rotation around the X and the Y, but in all the other directions, the user is free. So here, tau C, the constraint force is 0.
Okay.
It's the other modes, so the unicycle and the car-like, where we add...
Yeah, it was 50. Okay, yeah, I made a mistake. Sorry. Yeah.
So here in the video, you see that the user is able to rotate around Z and to move along the cutting direction. We also move vertically, but then it's the lateral constraint which is added here, so it's blocked with a hard spring. And when you rotate, also this lateral constraint rotates as well.
And your master arm is a virtuose in this case? Okay. And you don't have I don't remember what is the maximum torque for the user, the virtuose, to block the kinematic direction and it's the feedback, and it's the force feedback is really you can feel the constraints. You understand my question?
Yes. So we used a very high gain. It was, I think, around 500.
It was my question. You have understood it.
Yes.
So thank you.
Yes. So we used a very high gain, around 500, I think, if I'm not mistaken. So really, you could feel that you are blocked. You were not able to move laterally.
And you don't have any trouble with the stability again in that? You don't have any oscillation even with that?
No, we did not have in our system because, as I said, it was there was no delay, etc. But I think eventually a stability analysis could improve, of course.
Yeah, of course. But my question is, with a lot of experiments you have carried out, you don't have any trouble with that? You don't have any oscillation? No. Yeah. Okay.
Yeah, with all the users that we did. Yes.
Stable, very stable. Okay. So the slide number 55. So I'm not confident, but because maybe we discover the work during we have discovered the work during the presentation. But what you want to mention with new metric?
Yes. So the idea here is that we want to guide the user towards some learned trajectory, and we want to guide it not only based on the so there are already existing works which guide the user towards trajectory based on the variance from the learned data. So how confident the system is in the automation. But we want also an estimation of how well the user is performing so that the system adapts to the performance of the user. Okay. So if I start far, for example, then I know my user is a novice user and I need to give more weight to the autonomy. And vice versa. So the metric here is how, so we chose the Milano-based distance because it shows how far we are, but also it includes the variance. So it also includes how accurate the model is in estimating the desired trajectory. So
it's a linear distance? I haven't understood at the end.
It's the Milano-based distance.
Okay, perfect. Thank you very much. Maybe the last question about the scientific part. I am not an expert with the learning from demonstration, but the idea of using teleoperation data for that, for me, is also a nice idea. But I am not sure to have understood how you use that with haptic glove. Can you explain which kind of feedback you have and how you use that for the learning part? Yeah.
Yes. Yeah. So in this work, in terms of teleoperation, we had this haptic glove. So the haptic glove has 3 fingers, as you can see, and we have
which kind of
different angles, and we have.
Which kind of feedback do you have on these haptic gloves?
So you have 2 different motors which can. So you have the abduction and you have the proximal.
Yes.
No, so you have the proximal joint and the distal, I think. So yeah, there are 2 types. We call them the MCP and the PIP joint. So we have 2 joints.
Okay.
And they are mapped to the proximal and the distal of the hand. So on the hand, we have a set of tactile sensors on this part, the proximal, and on the distal. And then we use the proximal and the distal for here the MCP joint on the glove, and for the other joint we use only the distal values, which is from the extremity of the hand.
Mm-hmm. Okay. Okay. Okay, now I understand a little bit better. Okay, maybe for a few words about the future, because it's also important in a thesis to ask you a question about. So, can you show us the slide about the perspective of your work?
Yes.
So, you mentioned the next one, please. Yes. Yeah. So, I have basically two easy questions, but so okay, what you mentioned at the beginning is visual plus haptic. Okay, have you tried? Do you think an idea could be the use of illusion? Because of course it's of visual haptic illusion can be also a solution for this kind of application. I don't know if you know that, but a lot of work has been have been also carried out on visual haptic illusion.
So you mean like in a simulated environment?
Exactly.
Where you
exactly.
Feel like you're present?
Yes, because it's also the same question than Paolo about your visual feedback and how it's simple in this case, in your case.
Yes, so I think in actual teleoperation scenarios, so in our case, the user was directly present in front of the remote environment. So in this case, we did not need to add a virtual environment for the user to really feel there, because the user was really seeing it right in front. I think in other cases where there's an actual distance between the remote environment and the user, it would definitely be an addition. So if the user can use a simulated environment where they can feel there, and maybe see some augmented grasps to choose from, that would be, of course, interesting, yes, for future work.
And the last question, you mentioned cutaneous feedback or new other feedbacks. And do you have any idea about that? Or maybe, of course, it's always interesting to have other feedbacks, but have you an idea in mind behind that?
Yes, so why use cutaneous feedback, or what type?
Yeah, well, how it can help in the realization of the task for cutting or things like that.
So
we can take an example. Yes, cutting, for example.
Yes.
It will help us.
So in the cutting, for example, we currently design a system where we have very hard constraint for the user. So if we take a simple case of the lateral constraints, and we felt with the human studies that the user has a problem with giving the control to the system. So even though the system performs better, sometimes adding a lot of constraints make the user feel really not in control. So this was a problem that we faced with the users. This is why if we give the information, for example, using wearable haptics, so if we add a bracelet on the arm that would vibrate when the user is trying to do a lateral constraint, this way the user would know, okay, I am doing something wrong, I should not go laterally. But at the same time, he would not feel like, okay, I'm not in control. So the user would still be able to execute the task freely. So this is one possible idea that we have.
Okay. Okay. Again, I would like to congratulate for this work. It was really very impressed. A lot of contribution, a lot of work, a lot of collaboration, many papers. Congratulations again. Thank you very much.
Thank you. Thank you.
Thank you, Professor Stéphane Régnier. Now we will give the ground to Professor Dongheui Lee.
Yes. Hi. Can you hear me? Is it okay?
Yes.
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 Okay.
Yeah, thank you very much for the nice work and the nice presentation. Yeah, as other previous reviewers mentioned, it is really impressive work, and you really, given the short time, you really presented a lot in a best way as well. But yeah, so it was impressive, and then you had really a lot of collaboration, including our group as well, of course. And then I think one of the things is you did a lot of experiments also during this pandemic situation, also including user studies. So I think this is a great achievement. So I congratulate you and also the supervisors, Paolo and also Claudio, for that. So let me ask some questions. Maybe I will start with maybe question regarding the maybe first thing, the haptic, the feedback, basically. When you showed some examples about the, maybe it's the first one. So haptic versus the visual versus haptic visual feedback, right? You had it?
Yes, it was the first one.
Yeah. And then your evaluation metric shows that basically you compare the completion time and like the trajectory it followed, and then torque basically, and then the subjective metric, which is the likely level. Then here, obviously, right, the torque is much less when you give, or at least less than the visual cases, the less torque in the haptic cases compared to the visual feedback, right? But human prefer the visuals, right? Still over the haptics feedback.
Yes.
Why do you think it is like that? There is always a bit of gap between the qualitative measures and quantitative measures, right? How shall we tackle these gaps, right? Of course, we do usually both, but is there some way we are missing something to see some more quantitative data which tries to be matched to these subjective results? What do you think?
Yes, so it's true that users usually prefer visual data because we rely on vision for a lot of tasks, and because it would give them a better idea of what we're asking them to do. When you provide haptic feedback, maybe the user doesn't really know where the haptic feedback will guide him to. So the combination of both here gave the best results, but in the future, I think one possibility to improve the haptic feedback or to improve the acceptability of the haptic feedback from the users is to train them on it. So in this case, we got people who were not really experts in the domain. But if there's someone who is trained on the haptic interface for a long time, I think that this acceptance of the haptic feedback versus visual could also increase, because when you're trained on using this type of interfaces, then you know a little bit more where the system is trying to guide you. And I think this is one main point. So with time or with user experts, these results could change a little bit. Now, depending on the applications, the problem with visual only feedback also is that sometimes there's occlusion, so if you're relying really on the actual environment to give some visual information to the user, this is not always possible. So a good combination would be both together, but this is also not always possible. So it depends on what we want to do and what is the task at hand.
Mm-hmm. Yes, so I think often I don't know. So there are always a bit of tendency people rate more on the visuals, although if you lose some tactile sensation on your fingers or on the feet, also you might really cannot do a lot of typical, daily tasks and so on. So I think maybe although we use a lot, we have enough experiences in the haptics, I think. Mm-hmm. But this subjective questionnaire somehow doesn't really shows this the importance or how much really we are rely on.
Yes. So in this particular case, the questionnaire was how good were the feedback provided for you to be able to perform the task. Mm-hmm. It was not which one do you really prefer. So it was which method did you find more effective for you to know what you need to do. And this is why I think also when they see the visual feedback with the poses, I think this gives them a better understanding of what they need to do. But in the end, if we just choose which way is best to guide the user, maybe haptic feedback would be, haptics is always adds more information, and this is the intuition behind all the work here.
Okay, so in this case, the human was shown this monitors. Basically, human is seeing the monitor with many possible grasping points and with different weighting, right? So most likely ones are darker colors and so on, right?
Yes.
But do you think how we should design, in fact, the multimodal feedbacks in general? So everything going together is also a good thing, like visual and haptic, they are all important, but in some level, it might be becoming too much information to process as well, right? So what would be the clever way of designing, or let's say, in order to perceive this visual feedback, so a lot of feedbacks we're giving to the users, also increase another type of cognitive burden, right? Cognitive load. So what would be the good way of designing the feedback in your opinion?
So one way is, so as we did, for example, here, we started by showing the user the visual feedback in the beginning to give them an idea, in the case where we combined the two. And then during the task itself, the visual feedback was still there for the user, but they mainly relied on the haptic feedback. So this could be one idea where we decouple. So we start by showing one, and then we use the other, for example. Another idea could be to, for example, allow the user to just have haptic feedback, but then over time, let's say we have this simulated environment with the grasping poses. If the user feels like they need more information or more visual data, there could be a button to be pressed, and it could be user dependent. So when the user feels the need to more information, we could provide it to them. So this is one idea where the user would not be too overwhelmed with the information at the same time.
Okay, yeah, thank you. Maybe we move on to this authority allocation. So if I understood correctly, you are changing the authority in only the orientation around the z-axis, right?
Yes.
But you are calculating the confidences of the human and robot using XY motions.
Yes.
Yeah.
Yes.
Could you comment on it? Because what you are controlling, giving authority is a completely different space, but you are using the information from other spaces, right?
Yes. Actually, I am using the XY values for the confidence, but in the end, there's also some dependency on the angle of the trajectory with the X and Y. So I didn't add more information on the orientation because I felt it's redundant. But also here, the design, even though it's on the orientation level, the goal is to guide this user towards the trajectory, so in the X and Y. So it is the X and Y trajectory which I am interested in, but I only use the orientation to assure the non-holonomic constraint and to guide the user in a unicycle way to be able to go to the desired trajectory.
Yeah. Okay. So how long do you watch now to calculate this human's confidence? What is the time window you are looking into it?
So for now, it's the entire trajectory. So all the data is equally included in the metric of the human, but it could be changed. So it could be just a window over some past couple of data points, for example. So I think that would really depend on how much you want to include information. Is the first point where the user starts very important, or is it just over the time window that you want? For now, it's the entire trajectory.
But can you show us the maybe slide which calculates the CH?
Yes, so here it's the average distance over the entire trajectory, which is taken into consideration.
Okay. So all previous, okay, then I think maybe if you mentioning, right, as the motivation scenario, at least teaching the novice users to do some complicated task, right?
Mm-hmm.
Then the confidence level will be also changing in time, over time, right?
Yes.
So isn't it better to calculating this CH a bit, looking into the recent data, so that the course also can be updated?
Yes, I agree. So actually, for example, in the results, the preliminary results that we got, you can see that in the end, the human confidence does not change a lot, and it's mainly chosen in the beginning because we really have a dependency over all the possible data points. I think if we take just a small time window with the previous value, we could get more varying human confidence over time. So yes, if the user starts performing better over time, we could be able to catch it. I agree.
Okay, this calculation you are doing per each episode, right? You are not using it for the different episode neither, right? So at least this trial, you're calculating this confidence.
Yes, this trial.
Okay, yeah, I think it still is better than, of course, all the data from the all previous trials still. Okay,
Definitely,
so I can understand, of course, it's kind of more mainly done beginning, right?
Yes,
Mm-hmm.
of each trial.
Mm-hmm. Of each trials, it's more depend on how they are good, how good they are at the beginning, kind of determines this human's confidence.
Yes.
All right, yeah. Yes, I think it would be interesting to think about what is really good way of calculating these confidences, right? Is it all the samples are rated more or less equally, right? I mean, it's not completely equal because we are using the Mahalanobis distance, so there is a bit of effect. Yeah, maybe, yeah, that's it. So maybe you think the already important aspect points are already weighted by this, divided by these covariance metrics, right? So you kind of measures, of course, important parts are still into account, right?
Yes,
but accumulated one is kind of filtering out also.
Yeah. So important parts are taken care of based on the robot variance, or how good the data is, how sure we are that this is the trajectory that we want.
Mm-hmm.
And then over time, we add this human component.
Yeah. Okay. Okay, great. I have one more question around this actually. So how to handle unseen situations? That time, how to calculate the human's confidence and robot's confidence or autonomy confidence?
How to handle what? Can you
please unseen situations?
Okay. Unseen situations. So right now it does not handle. But if we want to add, we could add, for example, some estimation to. So if we know that this is a desired trajectory in the future, but the user is not doing it, then we know that there's an unseen situation, for example. In this case, maybe we want to give the user more input or more authority. Right now, this is not implemented. So we have one trajectory and we do not consider we have unseen obstacles. But then if we detect an obstacle, we can change the desired trajectory, or we can change the weight that we have from the variance, for example.
Mm-hmm. Yes, I think also this is very much related to the how to calculate this robot confidence part, so CR, in fact, because what you are looking into is only the variability in the data, right? But this variability says that it's just a variability among, right, what I have seen. But how much can it say how much I have experienced, how much this robot has the experience?
It's true.
Yes, it's only about the variability within the experience, but it doesn't say about the experience itself, right? Usually you have more experiences, then your confidence about the task might be increasing as well, right? So I feel these things are not yet tackled. Maybe, yeah, so this would be quite of an interesting point to think, yeah?
Yes. Yeah, I agree.
Okay. Then maybe we go to the last the topic, which was about the autonomous grasping, or at least help more. Yeah. So here, I think this was relatively quick for me, so I didn't follow so well. So I think maybe data itself, maybe how to learn. So you mentioned that there is a direct interaction by the human, and then the human directly, grasping the different objects, and you painted this object, so you find it out where the grasping points corresponding to the also human's hand, right? And then also you use the teleoperation data to learn the maybe each fingertips tactile data, and maybe also joint angles. Yeah, so finger configurations probably. But how do you combine these two information as a one? How do you, yeah, so my question is, how do you combine those two completely different sets of the training data set? That was a bit unclear to me.
Yes, so the way we combine is, so from the direct interaction, we got some heat maps that you can see here, for example. So we have the human hand, which was augmented with a heat map to show the contact areas. So this gave us an intuition about which sensors from the robot hand we want to use more or weight more in the learning algorithm. So then what we did is, of course, the human has 5 fingers and the robot hand has 3. So in the end, what we did, maybe it's clear here. Yes, it's small, but it shows it here. So we get this heat map and we transfer it by putting it over the robot hand. So we join each 2 fingers together for these 2 and these 2. And then we add these weights. So the heat map is added as a weight for the pressure sensors in the end for the learning algorithm. So this is how we know where to focus from a human perspective.
Okay, yeah. So, okay, great. Thank you. Okay. Yeah, great. Maybe I would like to ask maybe about the virtual fixture part. So, of course, there are 2 types of the virtual fixture you might be able to provide to the user's case, right? So which says that you shouldn't go there. And then I think this is done by now in your problem using this holonomic constraints, right? Very hard constraints you put it in. And then the guidance is done by the, sometimes done by the learning, or sometimes done by this, the calculating what would be the good trajectory to go based on your first 2 approaches, right? This the torques, accumulated torques after post-grasping, or this human's comfort. So I think these are some approaches. And have you thought about the different types of a bit of implementation of forbidden reasons?
Not in this, so not in the work that I presented. We mainly focus on virtual fixtures, guiding the user towards something. So even in the case of the cutting, where we had non-holonomic constraints, we had a direction which we tried to keep the user in. It could be interesting to think of forbidden regions, yes, but I have not implemented them for now in the thesis.
Yes. So in the one
for example,
yeah,
I was saying it could be relevant for the case of cutting, for example, to maybe try to implement it in a different way.
Yeah, because in some sense you combine the both also in one of your scenario, right? You had this unicycle motions, and then also you guided through the learning from the demonstration data. You did that, but maybe this is it possible to human can go away, not as really hard constraint, but I think it's a bit hard to go away, but you can also still go away from these reasons. I think if human wishes to.
Yes. This could also be interesting to maybe use this confidence of the human to tune the other type of feedback. Yes, it's possible.
Okay. Yeah, I think this goes more to the future research. Yeah. So yeah, I think that's all from my side. Thank you.
Thank you.
Thank you, Professor Dongheui. So before giving the floor to the supervisors, I will take the floor for a few minutes and for a few questions. First of all, I also join my colleagues to congratulate you, Rahaf, for your very clear presentation, but in general for your very nice work. It was very impressive. I really like two aspects in your thesis. First, your progressive approach. So you begin with a simple problem, and progressively you add different components, the satisfying the technical aspect, including the human factor, etc. And at the end, you go to the completely autonomous approach. And the second aspect that I really like is you try to satisfy two aspects: the technical aspect, the optimization of torque, etc., but the human factor aspect. And I think that for researchers in our field is very, very important. I was also I forget it, but I also thank you and want to thank the supervisors, Claudio and Paolo, for inviting me for this thesis. It was very interesting to discover your work and your team. Now I have some question about your work. So my question will be more on the human factor side, and I have also some general and philosophical questions. Paolo and Stéphane began talking about this aspect, but I need some details and your insight about this aspect concerning the evaluation of the workload. So for the teleoperation strategy that introduce user comfort. So you use the ruler approach. So the ruler is a set of ergonomic rules. I don't know if we can talk about statistical model, but this model or these rules are provided in a given context and do not consider the difference between peoples. Okay, because even two peoples, for instance, me and Paolo or Claudio, maybe we have the same morphology, but we have not necessarily the same physiology. Maybe more or less muscles or different cardiovascular system, or I don't know, different hormonal system, etc. And this leads to different perception of fatigue or constraint, etc. So you begin your report talking about this aspect, but do you think possible to include the difference between peoples in the design of your strategy or in the control of or the generation of virtual fixture?
Yes, so especially I think for the case of the ruler, for example, or the work which takes into account the human comfort. I think so. We use the ruler because it's a metric which is there and it's used a lot in ergonomics. But I think I also, I'm not sure if I mentioned it in the presentation, but we chose the ruler because it was a non-invasive method. So we wanted a method which works without any additional sensors for estimating the human workload. But I think to take into account this difference between users, it could be nice to use some EMG sensors, for example, try to measure the muscle force that's exerted. So this is one way to quantify more, if you want, the effort that's exerted by every single user differently. Also, another way could be, yes, to get some more data from different users using some learning algorithm, for example, or try to map different poses for the human arm with the perceived effort from the users and try to use this, for example. So even though we just used Joula here because it was a simple method which required no additional sensors, I think it could be interesting also to take into account this variability between the users in the future.
Okay. I don't know if you, because in your report you talked about some techniques using RGB cameras or not necessarily sensors, intrusive sensors, but and I don't know if you know the work of a team in Syria that developed this physics engine. Initially, they developed it for the simulation of mechanical parts, but they use it for a use case on the real-time analysis of human joint constraints. So with a simple camera and with this mechanical model, they can estimate the torque and the forces applied on the joint and the contact point, etc. So I don't know if this kind of method could be useful for your strategy or not.
I think so, yes. There's a lot of work which try to estimate using physics. Now, RGBD cameras, for example, could be interesting to get the exact value of the angles, because for now, we used an inverse kinematics algorithm which we implemented, which has many assumptions. So I think if we use RGBD cameras and get an actual position of the angles, then we can, yes, incorporate this using a simulator or some analysis which would give us directly the human workload. So yes, using physics, but then we would need maybe other values on the user itself, so the dimensions, etc.
Thank you. My second question deal with the virtual fixture and the haptic assistance. So in the past, I worked in the teleoperation. I think that Stéphane remember my work in teleoperation for micromanipulation. Now I am more on the human factors, but so when you provide virtual fixtures during teleoperation, so the human have to manage both the perception of the environment, the contact, etc., with the environment of with the object, etc., and the perception of virtual fixtures. Okay, so my question is, first, do you think that the virtual fixtures reduce the transparency of interaction and choose the level of presence of people in the remote environment, and is this constraining for both for novice users and for professional users? Because in your report you talked that the perception of professional and non-professional is different. So do you think that those virtual fixtures limit the transparency of interaction? I'm not talking about the quality of the algorithms. I'm talking about the combining the two perceptions at the same time. Is it relevant for users or not in terms of presence?
Yes. In terms of presence, so yes, if we just provide virtual fixtures, then of course we have decreased transparency and the user does not have a feel of what's currently going on in the remote environment. Now, combining them together would be interesting, but not always possible. So in the case of cutting, we had the two incorporated together. We had the virtual fixtures and the lateral motion, and we had some feedback from the environment in the cutting motion. And this way, we thought that the user could still feel what's happening in the relevant direction, which is the cutting direction. And in the lateral, there was the virtual fixture, which I think in all cases did not really decrease the transparency, because anyway, the user is not doing any lateral motion. So they don't need to feel the lateral motion. Yeah, so this is in terms of the cutting phase. I think also versus expert users, so the more the user, this is an idea that we developed by checking also the user data. So the users who were using the haptic device for the first time were not used to the type of haptic feedback that we give for guidance. So this is why we feel that with expert users, it would be more intuitive to provide this haptic feedback, and it would still be able to give some transparency aspect to the system. But this is of course to be proven with some experiments with actual experts.
Yeah. Thank you. So we remain in this the same topic, on the same issue. So the principle of using virtual fixtures is to stop wrong movement. maybe to reduce the fatigue, to improve the accuracy, etc. So the system generates an opposite movement that could reduce the fatigue, etc., or could use the wrong movement. So from my point of view, so this could be generate some fatigue. So since we are opposing the movement, okay, even it is a wrong movement, but we are generating opposite movement to a natural movement of people's. So I saw that you present different condition, haptic, visual haptic, etc., condition to the effectiveness of your approach and the guidance, etc. But do you think possible to prevent going on this wrong region before generating the opposite movement? I don't know, for instance, by using augmented reality display or different type of display, etc. I don't know if my question is clear or not, but how can we prevent people going or doing this wrong movement before generating those fixtures or this opposite movement that could generate some fatigue?
Yes, I see. So you mean instead of directly giving the user this haptic feedback, why not telling them this region is forbidden, try to avoid it, and if they do, yes, I think this would also work. Sorry, yeah.
Okay.
I think this would also work better, the forbidden region example, where we want to stay away from an undesired region. So this way, yes, for example, we could constrain the user in a smaller space, and this way, once they actually get to the forbidden region, we would give them the feedback. But I'm not sure this would work for the case of guiding towards a particular point of interest, because it's not really about putting them or pulling them away from a certain region, but more guiding them towards somewhere. So in this part, I think we need this feedback to the user to be able to guide them specifically to where we want to guide them.
Okay, thank you. So in chapter 6, I think in chapter 6, and I don't remember the slide in your presentation. This is not your conclusion, but this is my conclusion. So when you are talking about virtual fixture for cutting task, so my conclusion is that the best teleoperation consists to reduce. Sorry for my PC. About an hour every time. So the best teleoperation configuration consists to reduce more and more the number of free degree of freedom. So this is my conclusion. Not necessarily for all configuration, but so can we talk about teleoperation in this case, or and in general? Maybe this is a more general question. Do you think, because you're finding the last chapter that talk about completely autonomous approach, when you learn the gesture of grasping, etc., from real database, etc., you generate autonomous system. So do you think that the future of robotics will go more on completely autonomous approaches, or we in the future we always need the intervention of humans, and to put the human closely to the manipulation? And
yes, I think I don't think we're going towards a completely autonomous robotics in the future, in the very near future, because yes, we would like to automate some tasks like grasping food objects, for example. So this would be really good for the industry. It would decrease the workload on the user. It would make it more efficient. But I think in many cases we still need the human judgment. Like in the cutting, even though yes, we do constrain some directions of motion or some degrees of freedom, but it's still the user that's performing the cut. So in this case, we were not really trying to perform any autonomous system. And as I mentioned, in the case of teleoperation, sometimes we need to learn from the human how to regulate the stiffness, how to regulate different parameters. I think that the human still has some capabilities which are essential for systems. Of course, if we could incorporate them later on in autonomous robotics, then it would be nice. But I don't think we're close to doing everything autonomously. I think the user still needs to perform some tasks by himself.
Thank you. Concerning the last chapter, the haptic-based learning, so you use SVR model. First, why? Because there is a lot of model, neural network-based or neural approaches, etc. Why you use this model to develop to model the regression? And also, did you use the data that you collect for the grasping for human? So did you use raw data, or you apply some processing or pre-processing, or you extract some features or and use them for the learning? So why SBR, and did you apply some processing on the data before the training?
Yes, so why use SVR, not, for example, deep learning method? We chose SVR because it requires less trials. So, for example, for the teleoperation, we had the experts manually do the grasping, and it was very expensive to really do the task a lot of times for a deep learning algorithm. So we chose SVR because it gives good results, but at the same time does not require as much demonstrations. Same, for example, we didn't use reinforcement learning because also you would need to grasp different fruits many times and maybe ruin the fruits in the grasping phase. So we just chose a regression algorithm which works well. So we chose SVR. Concerning the data, so as I said, we had the human contact area, which was taken from the hand with the paint. Which then generated a heat map to be used in the algorithm. Then the data was weighted and rescaled. I'm not sure what you mean by pre-processing. If you mean more than that, or
filtering, or for maybe extracting some features before using the data, or
no. So the features are clear. We used the position, the orientation, the tactile information, and the heat map. So they were all used in the algorithm.
And concerning in the intervention of Yongli, you talked about combining two fingers. Yeah. Why this combination? Why you adopt this model? I understand that your robot has only 3 fingers, but why those fingers? Did you was you inspired by related work, or it was your idea?
No, so here we just used, so we simplified it because we needed a way to map a 5 fingers hand to a 3 fingers hand. And the way the robot hand was configured is that we had two, so we had the index and the middle finger with an opposing thumb. So it resembled the way that the human grasps if we have these 2 fingers put together. So this was just an intuition that we had to be able to superpose the 2 types of hand shapes. But of course, I think this is another topic in itself. So how to optimize this mapping between the human hand and the robots, which could lead to another topic of research. I think this was a simplification that we made in the work.
Thank you, Hal, and thank you again for this very nice work, this very nice presentation. And so now I will give the ground to the 2 supervisors. I suggest to begin with Professor Claudio Pascirotti first.
Yes, thank you. Thank you, Mr. President. But first, I would like, of course, to congratulate Rahaf for the great work that she did all these years. It was really a super cool journey. It was a very pleasure to work with Rahaf and with Paolo, of course, on these topics. For me, it was one of the first second PhD student. We started basically at the same time with the other one. I was the first one in this topic. Of course, I worked in optics before, but not on the shared control part. So it was also a way for me to discover together with Rahaf about all these interesting topics. And as we mentioned before, also the work of Rahaf was she collaborated with many different people, and I was always amazed about how she managed to always succeed, working in all these different environments and with all the different people, always in a successful way, which is not a given. And also very open and ready to embark in new journeys and opportunities. So she she worked using many different tools, hardware, the learning, the optics devices, the different robots, and always excited to start new things. Still remember when we almost sent her with a van to Paris with all the robotic system in the back. I think I never saw her more scared. But hopefully we found another way. And so she was always very positive and always very proactive in our research, in our collaboration. It was really a pleasure to work with her. And of course, this resulted in a huge and great amount of work, and so we did an amazing job. So I don't really have a question, and just more like a general wondering about. So we worked a lot on haptics, share control, but so nowadays we don't have neither haptics nor share control in the industry or in most commercially available systems, right? So what do you think is that, and what do you think we can do, and what, of course, what you did is part of this, to try to push a bit these technologies in the market, in everyday life, both for normal people and for the industry?
I think, so compared to, for example, visual information and visual feedback, which has been there for a very long time, I think that the haptics field still needs some development, some learning from the users on how to also design haptic feedback and haptic interfaces. So I think this is one of my points, that the visual systems were really developed for a long time now, and we're just starting to set up the haptics field. I also think it's about the user perceivedness. So as we said, the user is still used more to the visual feedback and some visual information. So I think we should also work on that. So how to train the users to be able to perceive haptics, because also it's a very interesting and useful type of feedback that we can use.
Well, congratulations again.
Thank you.
Yeah, thanks. So let me start by thanking again the jury, the committee, because I mean, first of all, you let's say, to the reviewers who took the time for reading the thesis, which is also not very short, and writing the report, and then of course taking the time today for being here for quite some time, and we are not done yet, and for all the good comments and feedback that you will give to Rahaf, that I think will be very helpful for her also in the following of her career. And yes, I not really so much more to say than what Claudio said. I would add that I also thank Claudio, because I mean, he supervised Rahaf more than me at the end of the day, so he was much closer to her during, interacting with her more than me during this year. So he was more present than me for sure. And so if let's say the work was successful, maybe a bit, some part of it is also thanks to Claudio, who provided a very good supervision to Rahaf. And Rahaf was really a great student. I mean, she was the second in my career. She was the second one from Lebanon that I had. And I had already a very good student before her from Lebanon, from the same university, and he was very good. And I thought, it was maybe one exception. But then now that I also Rahaf completed his thesis with great results, I have to say that I don't know, the education system in Lebanon must be very, very good, because all the students that we received from there, from that university, are so great and so successful. And she worked very, very hard, always with great care, always serious. And yes, I don't remember once that she said no to something. Like, we proposed many, when you are a supervisor, it's easy to propose many directions because you don't have to do the work. And yeah, she always said yes, and she tried with her best abilities to solve the problems, and really proposing solutions and working on the theory, but also a lot of the experiments, hardware. It's not a common skill that can be found in many PhD students, I would say, to this kind of ability. And I hope, I think that she has the right skills for a career in academia. I know that it's not very easy because it can be an uncertain career, and but I wish, I hope that she will be successful if she will have the desire of having an academic career. I think that she has the numbers for doing it. And just for the comedy, because I heard at some point, I don't remember who made the comment that she speaks a bit fast. I can assure you that during the repetitions, we told her many times to slow down. But, this must be the speed of her brain. It's like this.
I did my best.
And so yes, congratulations for all the work, and it was really nice to work with you during these years.
Thank you.
Thank you, Paolo. Professor Paolo, Rocco, maybe you have additional questions, or do you want to ask more questions?
Sorry, I was muted. Not really, but just maybe one. If you go back to slide 49 that I saw before, I was just curious about the. I mean, it's a very basic question. The control law, the robot control law, that is relates, as I understand, what is position of the. So what is on the right-hand side, and of course on the left-hand side there are talks, but so it looked like operational space error on one side and a joint talk on the other side. When you browse through these slides, I was captured by this equation that I didn't understood very well. So can you comment? How do you?
Yeah.
Yeah.
Here it's the Cartesian force vector, which we denote by tau, but it's not in the joint space. So it's a Cartesian impedance controller.
It's a Cartesian. Okay, now I got it. Yeah.
Yes.
Yeah. I thought that there was a joint. Okay, if it is a Cartesian,
no.
that makes perfectly sense. Okay, nothing else from my side.
Thank you. Paolo, we stay in the same session for the deliberation, or we have to use another link?
So the easiest thing is that now Rahaf will leave the room.
Yes.
And we just stay here so we can have our discussion, and then she will come back afterwards. Yes.
So I will leave from here also the meeting?
Yes, leave also from there, and
yes.
then we will tell you when you can come back.
Okay.
Stop, of course,
stop the streaming from YouTube. Yes.
you have to ask her because you have to be a little bit in a hurry if she's doing that. Okay.
I will ask her and let you know. Yes.
Yeah. Because it could be important for the delay, for the time.
Yes.
Okay.
Yes. Thanks.
So people are coming back, and we'll start the streaming again.
Yes. Good.
Just 1 second, and wait for the streaming to be started.
Donc, Madame Rahal, donc, on tient à vous remercier pour votre soutenance et pour la qualité de votre travail. Donc, je vais lire le rapport, donc, qui est la conclusion de notre discussion. Donc, le jury a apprécié les contributions et la qualité de travail de Madame Rahaf Rahal, portant donc sur le contrôle partagé et la répartition d'autorité pour la téléopération en robotique. Donc, ces travaux de thèse sont à l'intersection de différents domaines, la téléopération et le contrôle, l'interaction haptique et les études utilisateurs et bien sûr l'apprentissage automatique. Donc ces travaux de thèse ont notamment donné lieu à de nombreuses collaborations, notamment au niveau international. Madame Rahaf Rahal a présenté ses travaux d'une manière claire, bien illustrée et très pédagogique. Elle a su à la fois clarifier les problématiques et mettre en évidence les différentes contributions, à la fois théoriques et expérimentales. Ces travaux ont donné lieu à de nombreuses publications, dont un article qui a été récompensé. La candidate a répondu avec pertinence et avec conviction aux nombreuses questions du jury sur les différents aspects de la thèse. La discussion approfondie a montré une excellente maîtrise du sujet et un recul sur le domaine de la recherche plus généralement. Et donc, le jury s'est accordé d'une manière unanime à vous attribuer le grade de docteur en automatique productique et robotique de l'Université de Rennes 1. Et on tient à vous féliciter également pour vos travaux.
Bravo.
Vous avez aussi les félicitations du jury.
Bravo.
Bravo.
Merci. Should I talk? Okay, thank you.
Voilà, vous avez quelques,
So I would like.
Allez-y.
Yeah, so I would like to first of all thank all the jury members. Thank you for being here with us today, even if it's by video. And thank you for accepting to be part of my committee and for reading my manuscript and for also the interesting discussion in the end. I would like to say a huge thank you to my two advisors, Paolo and Claudio. Honestly, I really enjoyed working with you, and if I go back in time, I would choose you again because you were the most wonderful advisor that I could have chosen. I learned a lot from you academically. I also learned a lot on the research, on my potential, so you challenged me, you gave me some opportunities which were amazing, and I would really like to thank you for that. And not just on the academic level, so of course I learned a lot from you, but I also enjoyed our daily interaction, so thank you a lot for having accepted me from the beginning and for being always there for me during my PhD. This is why I'm here today defending my thesis, so thank you very much. I would also like to thank all of my colleagues and my friends here in the lab. Thank you for the people who are here today, especially, even though there's the lockdown measures. I really enjoyed the team spirit during the last 3 years, all the coffee breaks, all the events that we spent together. And you made these 3 years a lot more fun and a lot more interesting. Thank you especially for Julien, who helped me with the streaming today so that everyone can see. And I would also like to thank all of my friends from outside of the lab, from France, from Munich, and from Lebanon, and all over the world. I would like to thank again Professor Lee for hosting me for a short term, even if it was very fast. I really enjoyed working with you and collaborating with you and interacting with your lab members as well. And of course, I would like, last but not least, to thank my family. I wish that you could be here with us today to celebrate this together, but at least you got to see me through the streaming. A special thank you for my parents, who are the main reason why I'm here today, who have encouraged me a lot to pursue my dreams and to follow my potential. So thank you a lot, because you encouraged me during all these years. And thank you as well for my brother and my sister, who were also my greatest support during these years, during all the ups and downs of the PhD. So thank you very much for being there for me. And that's it. Thank you.
Thank you very much. And yeah, see you at some point.
Yeah.
Thank you, Paolo.
Bye. Thank you again.
Thank you. Thank you.
Thank you.
Ciao, Paolo.
Yes.
So we can stay on the
Bye-bye.
video for the live. Sorry? Maybe we can stay on the video for
Yes,
the
yes,
live.
Hey,
Done.
so,
Welcome.
C'est dans ton bureau. Elle est dans ton bureau. Je sais pas si on doit dire de là.
Should I stay there?
Mais c'est surtout pour la.
I think if you come here.
yeah, it's better here, yes. The camera is that one, I think. So,
Oh my god, thank you.
like on the thing set, you see your face.
Okay, this is
Peut-être une chaise pour les déballer, ça.
Félicitations, merci beaucoup, merci. Vous direz Laura pour l'atelier today. What should I start? Je commence par quoi? Pas ça?
Bah, vas-y, commence par ce que tu veux, c'est les tiens.
The more dogs to add to the collection.
How could you find the rainbow?
Congratulations.
We found the rainbow deck and the laureate deck.
This is wonderful, thank you. Should I do this or just let everyone's okay? Oh wow, okay, this is great. Perfect. Headphone.
Yes, when you have your meeting.
Perfect, yes. And no cancelling, it's perfect.
Exactly.
So you can stay near the train station with all the
Yes,
work.
and all the work that are going on. Perfect. Okay, this is also perfect. Le guide de survie, seul face à la nature. Le guide de survie face à la nature. Because I'm not a nature person. Camping, and it was a new, interesting experience for me. So thank you very much. I hope I will get to be more of a nature person. Okay, this is also perfect. So enjoy the tarot. Remind me of the times that we spent today this year.
Yeah, I forgot when we forgot when we were planning to send her all alone with the rope. With a big van.
I remember you with the said, do you have a driving license? I said, yes.
It was my first year.
Ran in Paris with a van. Hopefully we managed to find another approach.
Cool. It's also very useful for homework.
What is it?
I love that.
Lab test.
Thank you, guys.
Yeah. So, you have to work. This is
I have to work. To keep working.
In the lecture. You have to work in the lecture.
I can watch TV show on it.
Ah. Bon, merci beaucoup.
Ouais, en fait, c'est une carte cadeau pour, avec un montant pour aller.
I thought this is just like félicitations.
Non, c'est.
Okay.
C'est comme un bon, mais pour plusieurs.
Le bon n'est pas arrivé encore. C'est pas.
D'accord.
Merci quand même, merci beaucoup. Really for everyone for this. It's perfect. It's exactly what I would love to have. Thank you very much. Yes, actually, I wanted to take one.
Nice.
Thanks. Oh, I'm sorry.
Can we take a picture with everyone?
Yeah.
Right? Can you take a picture all together? A picture. Should we start?
Tu veux que j'arrête maintenant?
We can put the phone.
Wie das jetzt Kompliment doing other defense. Mais sûr, jetzt Kompliment.
Personne, ma collègue est